Welcome back to this lecture about EV battery performance parameters. The performance parameters of a battery are essential for safe and optimal operation. Before I will show how we can determine the performance parameters, we need to understand the basic working principle of the battery. Every battery consists of three main components: the negative electrode, the positive electrode, and the electrolyte. Other words for electrodes are the minus pole and the plus pole. The electrolyte is typically a liquid electrolyte, and together with the separator, it avoids a physical contacts between the two electrodes. Taking lithium ion as example, when the battery is charged, lithium ion are stored in the negative electrode, but they experience a driving force to migrate toward the positive electrode. The driving force for this is chemical, which means the lithium ion prefer to bond in the positive electrode material. The larger the bonding strength, the larger the potential in the electrode. And by combining the electrode with the larger bonding strength towards lithium with an electrode with a weak bonding strength, the difference between the two potentials is made larger. And this difference in potential is the battery voltage. Therefore, the battery voltage represents the chemical driving force for lithium to move from the negative towards the positive electrode. The atoms exist as ions in the electrodes. In the case of lithium, as the lithium plus, keeping their electrode density nearby the electronic bands of the host structure. Because the electrolyte does not conduct electrons, only the lithium ion can cross from one electrode through electrolyte to another electrode, and the electrons needs to go through the external circuits before recombining with the lithium ion in the other electrode. The electrons can travel through the external circuits to generate electrical current at this specific battery voltage. This means that the battery is effectively producing electrical energy during discharge, at least when the external circuits is closed via applications such as an EV. When all the lithium ions from the negative electrode have reached the positive electrode, the battery is full discharged and thus empty. The most important battery performance parameters are the capacity, state of charge, efficiency, energy content, the energy density, cycle life, and C rates. I'm going to explain those one by one. To understand the capacity, let's look at the voltage when the lithium-ion battery is discharged at constant and low current. The resultant variable voltage will look like this. The voltage on the average decreases during discharge because the lithium ions that have the largest chemical driving force, hence the largest voltage, will go first from the negative to the positive electrode. Horizontally in this graph, the capacity is shown. This quantifies the amount of charge that is passed during discharge from the negative to the positive electrode. It corresponds to the number of the lithium ions, each carrying one element charge unit that can be stored in the electrodes. How much lithium ions can be stored in the electrodes material depends on the detail on the electrode chemistry. For instance, graphite can host one lithium atom per 6 carbon atoms, whereas one silicon atom can host 4.4 lithium ions. The unit of charge is coulomb, and the elementary charge carried one electron or an ion equals 1.6 times 10 power minus 19 coulomb. The unit of current is ampere, which corresponds to coulombs passing per second. If we pass a discharge current during a certain time period, this corresponds to a specific amount of discharge capacity. For batteries, typically this is expressed as ampere hour, where 1 ampere hour corresponds to a current of 1 ampere during 1 hour, which equals 3600 coulomb. When the battery is charged at constant and low current again, the voltage will increase, typically the same way it dropped during discharge. The voltage increases as it will get harder and harder to move the lithium ions back to the negative electrode, where they are less strongly bound compared to the positive electrode. To determine how much battery is charged in percent, we can use the state of charge. 100% represents the fully charged state. In the same way, the state of discharge is defined. The efficiency of the battery can be divided into two different types. The Coulombic efficiency is the ratio between the discharge and charge capacity. It quantifies the ratio of electrons produced by a battery during discharge with that consumed during charge. If this deviates from 100%, this implies that some charge or discharge capacity is consumed by side reaction, where both the lithium ions as well as the electrons can be involved in these undesired side reactions. The other type of efficiency is energy efficiency. That is simply the ratio of the outgoing and incoming energy. The total amount of energy stored in the battery during charge and released during discharge corresponds to the average voltage times the capacity. More precisely, this corresponds to the area underneath the discharge or charge plot. Multiplying the unit of the voltage, volt, with the unit of capacity, coulomb, leads to the unit of energy, joules. In our figure of charge-discharge voltage versus capacity, this means that the area underneath the voltage curve represents the energy consumed during charge and produced during discharge. Because the capacity is typically expressed in ampere hours, multiplications with the voltage results in watt-hour, which is the unit most often used to express the energy content of the battery as we have seen before. For the conversion to joules, you need to realize that 1 watt-hour is the same as 3600 joules. The energy density is another very important parameter. There are two types of energy density. One is per weight and one is per volume. Now that we know how to determine the energy that can be stored in the battery, we can obtain the gravimetric energy density by dividing the energy content by the battery weight, resulting in the unit watt-hours per kilogram. The energy density per volume is called volumetric energy density. To obtain the volumetric energy density, we divide the energy by the volume of the battery, typically in the liters. The gravimetric energy density is most relevant for EVs, and the volumetric energy density for the portable electronics. We need to make distinction between the energy that is stored during charge and the energy that we get out during use of the battery. The ratio of these two is the energy efficiency of the battery. The energy efficiency of most batteries is relatively large compared to other energy storage technologies, typically above 90% for lithium-ion batteries. However, as we will see later, the energy efficiency depends on how fast we charge and discharge. Upon repeated charging and discharging, a battery loses some capacity. This is called capacity fading and is the main reason why batteries have so-called cycle life. When 80% of the starting capacity is left, the battery is often considered to be the end of its cycle life, at least for EV applications. In the next lecture, we will discover that the origin is the capacity fading. Up to now, we assume small charging and discharging currents. When the currents are larger, the observed battery capacity will change. Before looking into this, we have to quantify the charge rate. With the current expressed in amperes, we can control the charge or discharge rate and therefore how fast the battery is charged or discharged. Because the total charge or discharge time will depends on both the current and the battery capacity. The charge or discharge rate is often expressed in C rate, which takes into account the capacity of the battery. The Cx rate represents the current of charge or discharge the battery to its full capacity in X hours. For instance, C over 20 corresponds to the current that would charge or discharge the battery in 20 hours. 10C corresponds to the current that would charge or discharge the battery in 0.1 hours, which is 6 minutes. It is thus clear that higher C rates will lead to higher charging currents. Unfortunately, higher C rates come with a price, namely lower efficiency. Another unit frequently used is the specific current, the current normalized per gram or active electrode material. Let's have a look at how typical charge and discharge curve schematically looks at different charge rates expressed as C rates. The voltage during charge increases when we apply larger currents, and it decreases during discharge. This is the consequence of the internal resistance of the battery, the origin of which will be discussed in the next lecture. For very small current like C on 20, the voltage is typically close to chemical driving force, whereas the large current, it will deviate the current times the internal resistance. The voltage deviation is referred to as the overpotential. Note that the current I is negative during discharge and therefore is the overpotential is negative during discharge. Depends of the charge and discharge voltage on the current also has consequences for the capacity. This is because both charge and discharge capacities are restricted by the so-called cut-off voltage, V minimum and V maximum. This is to protect the electrode and electrolyte materials to degrade, which typically results in the shorter cycle life and lower energy efficiency, which again will be discussed in the next lecture. Now we establish the most important parameters that describe the battery performance and how they depend on each other. In the next lecture we'll look inside the battery in more detail. How these battery performance parameters depends on the battery chemistry inside.